Let's get started after our long delay. So today we're going to get into Aristotle's Metaphysics, but just recap off some of the important points from what we just finished, the organon. When we were ending the organon, we were talking about these basic axioms of logic that you can't deny, that you have to use in every field of study that you talk about. Right? Basic self-evident axioms. You can't prove them, there's no way to prove them. Aristotle says your mind is just so constituted such that when you come across them, you understand them. And you are more sure of these than you are of anything you could possibly prove, because you have to use these laws to prove. And then I completely failed to explicitly state what the laws were. Which I can't believe I didn't ever write that. The three fundamental laws of logic. The law of contradiction. A statement cannot both be true and false at the same time. It's impossible. The law of excluded middle. This one, some more picky mathematicians won't use. So you don't have to have it, but it helps a lot to have it in your reasoning. The law of excluded middle means that if I know that A is not true, then A is false. And if I know that A is not false, then I know it's true. In other words, there's no middle case. It's either true or false. And this is the logic that underlies like a proof by contradiction. How does a proof by contradiction work? We show it's impossible for it to be false, therefore it has to be true. So that's the law of excluded middle. A or not A.
Is that talking about things like it can be sometimes true and sometimes false, and saying that can't happen?
The law of excluded middle. The law of excluded middle says for any proposition we're guaranteed that we either have A or not A. That is always true.
So what if it's something like this sometimes true?
Oh, this isn't dealing with modal logic. They just don't use this. They prove all the exact same things that we do, not using that. They just never actually reference this. They don't say this is false. They don't say this isn't true. They say we're just not getting accepted as true, and we're going to work without it. Makes your life harder, but thus far they've been able to get pretty far not using it. So who knows? You might not necessarily need it, but it makes our life a whole lot easier to have it. So, and then finally, the last one, the law of identity. Everything is identical with itself. It's typically said in shorthand, A is A, typically written A equals A. A equals A. And with these basic identities, we can start to prove basic things about logic. So there was one that I kept saying to you guys over and over again last time. That's equals added to equals or equal. And that's just using the law of identity to actually prove that. It's something that we prove with these rules. It's not one of these rules itself. So if I know that A is equal to B, I know that A plus C is equal to B plus C. How do I prove that using the law of identity? Using the law of identity, I know that A plus C is equal to A plus C. Everything's identical with itself, right? And then I was also given that A is identical with B. So now I can replace that and I can say, so A plus C is equal to B plus C. So that's how we use identity to prove this. So if I know that A is equal to B, then that implies, this being true implies this is true, using the law of identity. And we just did a proof with that really quick. If I start with let A equal B, if that's given to us, then I know by the law of identity that this is true, this is always true, right? That's just using the law of identity. Now combine this with this gives me this, and it's proven. So this is something that's true in every single field. This is not limited to math. We did not have to put a plus here. I can put any random symbol there I want, and this is always the case as long as these symbols are still meaningful in whatever context you're talking about. So this is where we get our basic rules of arithmetic, some of our basic rules of arithmetic that you can add the same thing to both sides, subtract the same thing from both sides, multiply the same things to both sides, and divide the same thing from both sides. It's a law of logic. It's not a law of arithmetic. It's not a law of mathematics. It's a law of logic. It's more fundamental than that. And so these are the common, these three, and the things that you can build out of them are the common principles, common notions that every field, doesn't matter what field you're talking about, you can use these things. Doesn't matter if you're talking about biology, it doesn't matter if you're talking about physics, doesn't matter if you're talking about psychology, doesn't matter if you're talking about art. Any field of study you're talking about, you can use these things. They underlie reason itself. And you can't reason without using these things. Go ahead.
How does Aristotle deal with the law of contradiction in relation to the other philosophers like
So,
Heraclitus and Parmenides?
so the law of contradiction is what Aristotle has the most to say about. And since you can't prove these things, how is Aristotle going to convince you that you ought to accept the law of contradiction? And he gives you he lays out a bunch of ways that you could get someone who doesn't accept the law of contradiction to accept the law of contradiction. I won't walk you through all of them, I'll give you a sense of one of them. So one of the strategies is called affirmation by denial. This is one way that you could get someone to be convinced that they should accept the law of contradiction. It's called affirmation by denial. So, hypothetical conversation, someone comes up to you and says, I don't accept the law of contradiction. You say, wonderful, I'm so glad you accept the law of contradiction. They say, no, I don't accept the law of contradiction. It's not true. I'm so glad you're saying it's true. No, I'm saying it's false, so it can't be true. Law of contradiction. They're using the law of contradiction to try and deny the law of contradiction. Affirmation by denial. In their attempt to deny it, they're using it. You can't reason without using the law of contradiction.
So how about the philosophy though? Like everything's changing.
Well, we'll see what he says about change in particular. That's a much higher level thing, because that has to do with physical things in this universe.
But we will see him get to that.
But we will see him. So Heraclitus denying the law of contradiction, allowing contradictions, no. You have to use the law of contradiction to even kick off reasoning. The only way that you can deny the law of contradiction is if you refuse to reason. And Aristotle says, well, if you refuse to reason, what difference is there between you and a vegetable?
That's fair.
And why would you argue with a vegetable? So if someone refuses to reason, move on. So, fundamental to every field, can't get away from them. Some people think maybe we can make do without that, maybe not. For the sake of Aristotle, here's what they are and what we typically use in logic currently. Okay. Now, going back to one more fundamental notion in his categories, not his categories, it wasn't his categories, but in his working on, were these four types. So this underlays so much of his metaphysics, we need to remind ourselves about these four types that we talked about 100 times. The not predicated, not in, predicated, not in, predicated in, and not predicated in. Remember these four categories?
Yeah.
Let's briefly remind ourselves of what each of these categories are. What's this first category? Give me intuition for this first category. I'm a first grader, I don't know what this means. Tell me what this means.
Primary substance or individual substance.
It's like the particulars of more physical stuff.
Any concrete thing in reality you can go touch. This is a primary substance. This is a primary substance. This is a primary substance. Anything I can touch is a primary substance. Every physical, individual, particular thing. Make sense? Now, secondary substances, this category, were universals whose instances are things you can go touch. Man falls into this category. Man is a secondary substance because it's possible for me to go touch a man.
Yeah.
Red does not fall into this category. I cannot go touch a red. You have to say a red what? You need it to be in something. So it's going to be this category down here. It has to be in something to exist.
Okay.
So this not in, we don't have to require this to be in something to exist. This not in, we don't have to require it to be in something to exist. These two are in. So this category, this is man, this is animal, this is marker, this is light bulb. Anything whose instances are a physical, particular thing.
Okay.
Universals whose instances you can go touch. These are the things you can go touch. These are universals whose instances you can go touch. These are universals whose instances you can't go touch. Like red, like walking. I can't go touch a walking. I can go touch a walking bird. I can go touch a walking cat. I can't go touch a walking. Make sense?
Yeah.
Okay.
And then finally we had not predicated, not in. So not predicated means it's not a universal. And, sorry, I said not in, but I meant in. Not predicated means it's not a universal, so we're talking about a particular. And in means it has to be in something to exist. This would be like my memory of yesterday. My memory of yesterday is a particular memory, but it doesn't exist independent of me. You get rid of me, you got rid of the memory. It's dependent on me for its existence.
What are other
It's
things?
not its own individual thing. It's often going to be intangible things like that. Okay, and so this is a classification, not of all the things we see in the world around us. This is a classification of every thought, concept, idea, word. Any word you can assign meaning to falls into one of these four categories. Make sense? Okay, now notice how everything here is dependent upon this category. Your universal primaries. Everything is dependent upon this category for its existence. When we talk about secondary substances, these are classifications of these things. That's all they are. They're groupings of these things. If there's none of these things, there's no grouping of those things.
Yeah.
Right? And then these two, notice that they have to be in something to exist. If we get rid of the somethings that they can exist in, they no longer exist. If there's no individual particular things, there's no more red. Red only exists in things. Red doesn't exist in the ether by itself.
Okay.
Running only exists in things. Running doesn't exist in the ether by itself. So everything, every concept, idea, notion that you have is dependent on individual, particular things in this universe. All knowledge, all ideas, everything is dependent on individual particulars. Now this is drastically different from Plato's system. Remember, it's Plato's system. There's the world of forms, the world of universals, and we're just a shadow of that. And so we're dependent on the universals for our existence. Aristotle's saying backwards. Universals don't exist without us, without the individual particular things. So he's flipping Plato's system up on its head. So note that primary substances are prior, using it in that dependent upon for existence. Note that primary substances are prior to everything else. Everything else is dependent upon primary substances to make sense of, to exist, to be reasonable. Everything else is dependent on them for its existence. Not only is no D there, not only is an individual particular its own thing now, but it's a type of thing. It is a particular of a universal. So now we're moving forward. So this whole part, just to hammer home, primary substances are what's primary. That's why they're called primary substances. Now, for any primary substance we could talk about it in two different ways. So let me grab, well, we'll move on to, how do I want this? Let's move on to the next slide to hammer home what I'm saying in this next part. So for any individual thing, it's a universal, it's a particular of a universal. This is a marker. Marker is a universal, but this is a particular of that universal, right? This is a marker. So it's an individual thing of a universal. Notice that this is a marker and this is a marker, but these are two different markers. They're not the same marker.
Yeah.
So every individual has a form. These both have the same form, they're both markers. But they also have matter. The matter of this marker is not the same as the matter of this marker. That make sense?
Yeah.
And so, we're going to say the form is what makes things common. It's what's universal to things. It's the universalizing element in everything. And matter is the individuating element. Trying to say that. Individuating element in everything. What makes this the same as this? They both have the form marker. That's the universal that they have in common. What makes this different from this? They have separate matter. The matter of this is not the matter of this. So Aristotle is saying that anytime we're looking at an individual particular thing, It has a universalizing element, that's the form it has, namely this is a matter, this is a marker. And it has an individuating element, which is the matter that composes it. That's what makes it separate from everything else. And the form and the matter exist together right here in this ink. The form of this doesn't exist in some universe out there. The form of it exists right here.
Can multiple forms exist in one particular thing?
Yes, so any universal you can apply to this ink is a form it has. This is a capped object. We can talk about the universal all capped objects. This is a capped object. This is also a marker. This is also a writing utensil.
I see.
Those are a bunch of different universals, a bunch of different forms we can say this thing has. And the matter is what it's composed of. I can say it's composed of plastic. That's its matter. I can also say it's composed of atoms. That's its matter. I can also say it's composed of protons, neutrons, and electrons. That's its matter. So there isn't the right form to say that this thing has, and there isn't the one right matter to say this thing has, but it definitely has some form and not other form, and it definitely has some matter and not other matter.
Okay.
Make sense?
Yeah.
Okay, so fundamentally, every individual is composed of matter and form. The matter is what makes it this thing as opposed to that thing. It's the individuating element. And form dictates what type of thing it is. Based on its form, you can say it's a marker. Based on its form, you can say it's capped. Based on its form, you can say it's a writing utensil.
Yeah.
Okay. Example, marker B. We already talked about that. And then you might have said, you might take an issue when I show two markers and said, yeah, but those aren't really the same form. This is a purple marker, this is a pink marker. Maybe this one's a little bit bigger than this one. But when we think about electrons, using our modern notion of electrons are actually identical. Completely identical. No electron is slightly bigger than another electron. They're identical in size. So two electrons are completely identical, and yet we have this electron and this electron. What separates them? What makes them two individual electrons instead of the same electron? They have different matter.
Okay.
Good?
Yeah.
Okay. Now, two things to know about matter and form. First thing to note about matter and form is these are relative terms. The form and the matter depend on what you're talking about. And it's like when we were talking about genus and species. So if we go back and we have here's a set of all plane figures. That's an A. Plane figures. Here's a set of all plane figures. Well, inside that set, we can define something called a triangle, right? And that's a subset of plane figures. Plane figure is just a figure you can fit in a plane. A subset of that is triangles. And we can come up with a definition to define this species. Namely, we can say, take all your plane figures that have 3 sides and 3 vertices. Where we define a triangle as a plane figure with 3 sides and 3 vertices. Right?
Yeah.
And so we just created a species from this genus.
Yeah.
And I could go further and I could define equilateral triangles. So we have our definition for equilateral triangles right here. And I say an equilateral triangle is a triangle with 3 equal sides. Make sense?
Mm-hmm.
So then equilateral triangle is a species relative to triangle. Triangle is a genus relative to equilateral triangle. Plane figure is a genus relative to triangle. Triangle is a species relative to plane triangle. And so you see how this triangle is acting both as a species and a genus.
Yeah.
In like manner, an object can act both as form relative to one thing and matter relative to another. So let's look at an example really quick. If we were talking about the matter of this classroom, you notice that the walls of this classroom are made out of bricks.
Mm-hmm.
So part of the matter of this classroom is a brick. So a brick is matter relative to this classroom. But then when we look at this particular brick, let's pretend we know it's made out of concrete. Now this is concrete in a particular form. So now brick is the form of the concrete, the matter.
Yeah.
So with respect to the classroom, this is matter. With respect to the concrete, this is form. It's a relative term.
Okay.
Make sense?
Yeah.
The other thing to know in how we're talking about matter and form here that might be a little bit off from your intuition is Aristotle is not necessarily limiting this to physical things that we can touch in reality. So let's look at another example where we would use matter and form. Look at these two statements, these two arguments. Top argument. All men are mortal, Socrates is a man, therefore Socrates is mortal. Next argument. All cows are animals, Betsy is a cow, therefore Betsy is an animal. You see how these two arguments have the same form from that table we looked at last time?
Mm-hmm.
But they have different words in there. They have different matter. Same form, different matter.
Okay.
And if I were to use identical words here and identical words here, you say I listed the exact same argument twice, because now they have the exact same form of matter. Right? Okay. So we're not necessarily just talking about physical things. That's the majority of what we're going to talk about here. Just be clear that Aristotle is using this in kind of a broad sense. How we have our current notion of matter obviously comes from how he's using matter, but he's using it in a broader sense than we're used to using it today. Think we're good there?
Yeah.
So, I guess I got a pretty elaborate example to make sure you understand how they're relative. When I think a house composed out of bricks, the house is the form relative to the matter of the bricks.
Yeah.
So there's the form, there's the matter. When I think bricks composed of concrete, now bricks is the form, concrete's the matter. When I think about concrete composed of atoms, atoms are the matter, concrete's the form. And then I can think about atoms composed of protons, neutrons, and electrons. You know that's what goes into making an atom. So protons, neutrons, and electrons are the matter of an atom when they're in that particular form. Put together in a particular form, you now have an atom. Furthermore, we know that protons and neutrons are composed of quarks. Right? So quarks are matters for protons and neutrons. How far back can we go with this process? How much can we keep reducing it? Finding more fundamental and fundamental matter to work with. Lower and lower level matter. Can we get down to just pure matter? Is there such a thing as pure matter in the universe? What do you think?
I think it could be possible.
It's down to just pure energy.
Pure energy? What do you mean by that? You mean photons? Photons are particular things. That still has a form. We call it a photon. Just matter with no form. Is there such a thing? Aristotle says no. There is no such thing. So you can't get back to just pure matter. Now we may eventually use the word prime matter, which he uses to say the matter that underlies everything, ultimately. But he says there's never just prime matter somewhere in the universe. You can never just go find prime matter, matter without any form. What would it be if it has no form? Forms are how we know things. What could you know about prime matter if it has no form?
Okay.
It couldn't fall into it couldn't fall into the category of sensible things. Because that's universally applied to it, that's some form it has. So you have to eliminate it in every possible way from being knowable by human beings if it existed. So he thinks it doesn't exist. And we'll see another argument for why he thinks it doesn't exist a little bit later. A more compelling argument than that one. Okay, so roughly speaking, what's matter? Matter is anything we can impose structure on. If I can take it and give it some structure, we call that matter. I can take bricks and I can put them together in a house. I can take bricks and I can put them together in a pile. So bricks would be constitute matter. I can impose some structure on it. What's form? It's any type of structure we can impose, or it's any universal. Every universal is referencing structure.
Okay.
So would that be a form?
Yes. That thing is so structured as to appear red to your eye.
Can you have different kinds of matters in form?
Can you have different kinds of matters? Yeah, look at this classroom. It's not just composed of brick. It's also composed of carpet. That's also matter relative to this classroom. Brick is just one of the things that goes into it. Good?
Yeah.
Okay. So now let's jump to what you were talking about, dealing with Heraclitus and Parmenides. Because remember, it's been a long time since we mentioned this, but remember that man way, way back by the name of Socrates. Right?
Yeah.
What was he out to do? He was out to argue with these. Basically, a lot of people tried to deal with Parmenides and Heraclitus and put them together in a way that was coherent. And it kept falling apart no matter how they tried to do it. So you have the sophists come along, these skeptics who says, no, there's no such thing as objective truth, reality, blah, blah, blah. It's all in the eye of the beholder. right? And then Socrates came back on the scene and he says, no, there's absolute and objective truth, absolute and objective beauty, absolute and objective good. And he started Plato and Aristotle. So Plato and Aristotle were trying to stay true to Socrates, keep the objective good, true, and beautiful, while solving Heraclitus and Parmenides. So that's what Plato was trying to do with his elaborate system. Aristotle says, love what you're trying to do. Your system's garbage, though. So he built a new system trying to do the exact same thing from a high level. Make sense? So ultimately, we're still trying to deal with Heraclitus and Parmenides. That's a huge part of what we're doing. And then, obviously, Aristotle goes way beyond just dealing with those two. But one thing he has to deal with along the way. So what does Heraclitus say? Heraclitus says, change implies a contradiction. At the end of the change, it both is and is not the same thing.
Yeah.
So if I got Tim, my caterpillar, and he turns into Tim the butterfly, then I had Tim before, and I have Tim after. So I still have Tim. I still have the same thing. I didn't switch up Tim and replace him with Betsy, who was a butterfly. It was Tim the whole time. So I still have Tim. I still have the same thing. But then, before I had a caterpillar, now I have a butterfly. That's not the same thing. Those are different animals. So it both is and is not the same thing. So it is the same thing since it was changed. Since it was changed and it wasn't replaced, it just changed. And it isn't the same thing since it changed. If it changed, that means it's not the same as it was. It changed. Right? So there's a sticky situation. Aristotle says, you're absolutely right, Heraclitus. Aristotle agrees that after a change, it both is and is not the same thing, but in two different respects. Aristotle says, you're right that it's not the same thing in the sense that it doesn't have the same form anymore. You're wrong, though, because it still has the same matter. Oh, he says you're right in regards to both things. It is the same thing because it's still the same matter, and it's not the same thing because it's a different form. So yes, you can say it both is and is not the same thing, but if you were to say it more clearly, Heraclitus, you would say, it is the same matter, it is not the same form. Where's your contradiction now? Nothing wrong with saying it's the same matter in just a different form. There's no longer a contradiction in that statement. Make sense?
Okay.
So when an object changes, its form changes, but its matter stays the same, typically depending on what you call the matter. You need to make sure you go on low enough level. But so when a caterpillar turns into a butterfly, it's still the same cells, it's still the same organs, it's still the same little thing there. All the matter that was in there is still the same. Right?
Yeah.
And it's just the form of that matter that changed. So still the same matter, just a different form. That's all that happened. So it is the same thing because it's still the same matter. It's not the same thing because the form changed. But that's not a contradiction.
Can this change be not just be physical, so it can be any sort of change ever?
Change is inherently physical, so I'd have to get an example of what you mean. It could be as simple as hitting a ball. It could be building a chair.
In a sense, your mind changes or matures over time, right?
Oh yeah, we'll talk about that exact process of you learning.
Oh, okay.
Yes, that is one of the changes that we will talk about. But you'll have to wait till we get to psychology to talk about how your mind changes and how you become informed as your mind becomes more formed as it takes in forms. Okay, but yeah, so good point, that isn't physical, that's psychological, but yeah, right now we're just talking about the physical stuff.
Okay.
Go ahead.
What if it gets bigger or smaller?
Okay, so that's why I said typically here, because you need to make sure that you reference all the stuff that was involved in the process. So if I'm the caterpillar and I'm a big fat caterpillar, I don't know if building the cocoon actually comes from like inside them. I think it does, right? So I'm a big fat caterpillar. Some of my matter changed form from caterpillar to cocoon, and some of my matter changed form from caterpillar to butterfly. But everything's still accounted for. There's no new matter that suddenly came into existence. And there's no new matter that suddenly went out of existence. All that happened was matter changed form, and that's it.
But when you take the chair, you're just taking the different pieces of legs and stuff, pieces of wood and putting them together.
Right. So that's an easier example to follow. Biological examples are harder to follow. If we think about a pile of wood, so I got a pile of wood just laying there, and then I put together in the form of a chair. I just changed it from a pile of wood to chair. Exact same matter, we still have the wood. That's wood is matter relative to that change. So we still have the exact same wood. All that happened was change the form. It went from being in the form of a pile to a form of a chair.
Okay.
Or maybe I take apart a table and turn it into a chair.
Yeah.
Still the exact same wood. Before it's in the form of a table, now it's in the form of a chair. Same matter, different form. That's all that happened. Good?
Yeah, that makes sense.
Cool. So, that was one of my examples. And then a ball moving. Might seem a little bit weird for us to take this into consideration in the form, but Aristotle does. This being 1 meter in the air is part of its form. That's a universal we can apply to this thing. All objects 1 meter in the air.
Okay.
So then when I drop it, it went from being in this form to being in this form. One of the objects on the ground. However you want to say that.
Okay.
So even simple changes like an object falling is just changes in form. Same matter, different form.
So moving position.
Moving position is still considered change in form. Its position can be part of its form. Because you can universalize position. You can talk about all the objects that are at such and such a position. So if you can universalize it, then it's captured in its form somehow.
Does time count as one of these forms?
Time, where it is in time, sure. Not quite sure how to work with that one, because Aristotle's definition of time is the measure of change. Time is measuring change. And so time isn't part of the form of something. Time is measuring forms changing. So time measures motion, is the simplest way to say it. So Aristotle says time measures motion. If you stop all motion, there's no more time. And think about how he says time measures motion. It's what we do all the time. What's a year? It's measuring the earth going all the way around the sun. What's a day? Measuring the earth spinning like this,
Yeah.
etc. So we measure our time off of motion. You think about a grandfather clock. When does it tick? When the pendulum goes back and forth. Or maybe it ticks every swing, I don't know. If it has to go back and forth or if it's just one swing. But whatever it is, measuring the motion. So it's a fairly intuitive idea. We don't really think about it that way, but you can see how that's intuitive. And I think that's how Aristotle defines it. So time would not go in the form since time is measuring the change of form. Good question. Okay. So we talked about that. So change, rough definition of change, the process by which matter takes on a new form. We can roughly use that as our definition for change if we want. Note that with this definition, there's no longer a contradiction inherent in change. We no longer have what is becoming what is not and what is not becoming what is. We're not saying something is both A and not A. We're saying the matter was A and the matter still is A. And we're saying the form was B and now the form is C.
Okay.
Okay. So now let's deal with Parmenides really quick. What does Parmenides say? Parmenides says there's no change since you have what is becoming what is not and what is not becoming what is. Aristotle deals with this in a very similar way. Aristotle says no, with change, the matter, the most basic matter, in its most fundamental sense, always existed. It just changed from being matter of one form to matter of another form. Nothing new really came into existence or went out of existence. Because remember, Parmenides, when he's talking about what is, he's talking about being, he's talking about what exists.
Yeah.
You have existing things going into not existing, and non-existing things coming into existence. Aristotle says no, you have the same matter, just persists. Never went out of existence, never came into existence. So, that's how he deals with Parmenides. Any questions about how he deals with those two?
No, I'm glad we finally got to that.
It's taken like 300 years.
Yeah. I don't have a rough date on Aristotle. I don't remember our years. But yeah, I wouldn't be surprised if you're pretty close to right on. Okay. So, there we go. We've dealt with Heraclitus and Parmenides. So for Aristotle, our world is both a changing world and it's an intelligible world, a world that we can understand. The forms are right here around us, which are the things that we understand. And the individual things, yeah, they do change. That's perfectly fine. So changing your world and we can understand the world. Remember, going back to Plato, Plato thought we couldn't really know this world. We can know the unchanging, perfect world of forms. Yes, that we can know. But in this world with change, we can only have opinion at best. We can't really know anything. With Aristotle, nope, you can know it. You can know it just fine. You can understand this world that you're a part of. Which you can see why he's the father of science. Because science is how we come to understand this world. So the world is as it seems, for the most part. Obviously there are exceptions, but he's saying this isn't one big delusion. It's not one big dream. You're experiencing reality. It's real, and you can understand it. And it can be understood in a manner compatible with the way it seems. So the world is the way it seems. It's a changing world, and you can understand it. And there's nothing wrong with that. We're not breaking any rules of logic. Not only does change not contradict the laws of logic, but change presupposes the laws of logic. And we've already talked about this earlier, how any attempt you have at reasoning presupposes the laws of logic. You can't get around from it.
Yeah.
You can't get away from it. Around from it. You can't get away from it. So how does change presuppose the law of contradiction? Well, change says it was A and now it's not A. Right? That's what change says. Change says it was A and now it's not A because it changed in some sense. And so if it is A and not A at the same time, then it didn't change. Right?
Yeah.
Yeah.
Okay. And then it presupposes the law of identity, the principle of identity here, because we talk about one thing changing. If it didn't have some identity and I says, watch, I'm going to turn this chair into a rabbit, and I throw the chair and grab a rabbit, and I say, ta-da! You say, no, the chair's right there. You have to use identity to talk about change. So you can't get away from it. So he says, targeting Heraclius a little bit more here, not only does change not imply contradiction, but you have to assume it doesn't to even talk about change meaningfully. When changing, an object goes from being A to being B. It changes identity. Just explain exactly what I said there. Okay. So now, going back to talking about particular things, matter and form. A particular has matter and an actual form. Now it's possible to change the form that the matter is in. Going back to thinking about a chair. Chair composed only out of wood. So it's possible to change the form of the matter into another form. So I can take my chair, completely made out of wood, and change the form so now it's a table completely made out of wood. Assuming I perfectly preserve the wood. You with me so far? Okay, so the different forms that the matter could, keyword there, could take on, are its potential. If I have a wooden chair, I say this is potentially a table. Or if I have a pile of wood, I say this is potentially a chair. It has the potential to be a chair.
Okay.
And that only makes sense when it isn't actually a chair. Okay? The next two keywords we're going to talk about here are potential and actual. So the four keywords that you get with Aristotle's Metaphysics are first matter and form, and then the next two are potential and actual. What it could potentially be and what it actually is. And we almost use potential and actual exactly how Aristotle introduced them way back when. So for this, our language almost matches up perfect with Aristotle's ideas of these words.
Okay.
So this one's not as weird, and we already have basic notions of what we mean by what something actually is and what something potentially is. So I feel like I'm over-explaining here on this one since we're already pretty comfortable with these ideas. The form the matter currently has is what it actually is. So what actually is its current form. What it potentially is forms it could potentially take on. It could take on. Try and not use the word potentially when I say it. Okay, so let's look at example. Let's look at an acorn. Now, an acorn, that's an individual thing. It's form and matter, right? Now, based on its form, based on the fact that we know it's an acorn, the fact that the matter's in that form, it's in the form of an acorn, we know that it is potentially an oak. It's not potentially a sunflower. It's not potentially a cedar tree. It's potentially an oak. Its form dictates what it potentially is. It can potentially be some things, and it cannot potentially be other things. I cannot plant an acorn and grow a cedar tree. I can't plant an acorn and grow a Jeremy. I'm very limited what I can do with that acorn. So that acorn is potentially an oak, and it's also potentially decomposed organic matter, whatever you want to call it. I could plant the oak, or I could plant the acorn and grow an oak, or I could leave it in the gutter and it slowly withers away. Two possible outcomes for that thing. but notice that it's limited in what it can potentially be. And, well, that's all I need to say.
So the
based off of
form's
its current
limited?
form. Based on its current form. Based on what it actually is, limits what it potentially could be.
But once it goes into something else, then those limits change.
Correct.
Okay.
So water is not potentially a chair. You cannot build a chair out of water. You can take the water, freeze the water, chisel a chair out of it. And so ice is potentially a chair. Water is not potentially a chair. Water is potentially ice is potentially a chair, and yes, you can think about a string like that.
Okay.
So once again, it's relative to its current form. What could this be matter for is another way to say it. When I'm sitting on a chair out of ice, I don't say this chair is made out of water. We might say it's made out of water molecules, but I mean water as in the liquid water, as in its state of matter, not the element, or compound. So with liquid water, you can't make a chair. I can never have a chair made out of liquid water. I could have ice made out of liquid water, and then I could have a chair made out of ice.
Yeah.
Okay. So an acorn is a combination of form and matter, and based on its form, we know that it's potentially an oak and is also potentially decomposed organic matter. It is not actually an oak until it takes on that form. So when I hold an acorn, I'm not holding actually an oak. I'm just holding an acorn. An object's actuality dictates its potentiality. What it actually is dictates what it potentially could be. A pile of wood, what it actually is potentially a chair, what it actually could be.
Yep.
Over-explaining? Okay, so going back to our earlier example, now we run it backwards. Quarks are potentially protons and neutrons. Protons and neutrons and electrons are potentially an atom. Atoms are potentially concrete. Concrete is potentially bricks, and bricks are potentially a house. So you see how potentiality and actuality are very closely related to form and matter, following that same chain. Cool. Okay. Crucial point, I've said it 100 times. Since a potentiality is a form not currently possessed by an object cannot be potentially what it actually is.
Yeah.
This is getting ready for his argument that there's no prime matter that exists in the universe. So, if it's potentially it, it can't actually be that thing. If it's potentially that thing, it can't actually be that thing. Okay. Now, since everything in the universe is ultimately composed of matter, right?
Mm-hmm.
Because if it's a thing in the universe, it's an individual, which means it has matter. So everything in the universe is composed of matter. So I can use matter to construct anything in the universe, because everything in the universe is ultimately matter. With me so far?
Yeah.
So then pure matter would be potentially anything. Right? If everything in the universe is made out of matter, then with pure matter, I should potentially be able to make anything. Because everything comes from matter. You with me?
Mm-hmm.
Okay, so since pure matter would potentially be, since it's potentially anything, then what is it actually? Nothing. Because it can't be potentially what it already is. You can't be potentially what you are actually. So if you're potentially anything, then you can't actually be anything. So you have to actually be nothing.
What if it's like an atom? Doesn't that make anything?
No. I can't use an atom to construct a photon. An atom relative to a photon is like using this whole school to construct a pencil. It's a big, complex, messy things with lots of subatomic particles. And you have different fundamental particles. You have an electron and you have a proton. Or electron and a photon. And sometimes an electron goes out of existence and then we have a photon. And then the photon goes out of existence and now we have an electron. But we can't, in physics, we can't look at it in some transition period. And so anytime we observe a fundamental particle, it's a fundamental particle. It's a particle of some type. So, if it's potentially anything, it's actually nothing. And nothing doesn't exist. So that's his more sophisticated argument for why there's no such thing as matter without form. Matter without form would be potentially anything, and therefore it would have to actually be nothing.
Okay, that makes sense.
Okay. Therefore, there's no such thing as pure matter. I'm going to accidentally say prime matter a lot of the time. Pure matter, prime matter, same thing. Aristotle uses the word prime matter. And so everything in the universe has both matter and form, with one exception. And we'll get to that exception later on. There's one thing that doesn't have both matter and form. And if it's not pure matter, then it must be pure form. And we'll get to that. Okay, so another way we can think about change then. Change is a passage from potentiality to actuality. When an object changes, it changes from potentially being something to actually being that thing. Another way we can think about change. Okay, yeah, makes perfect sense. Okay, so when a seed grows into a flower, it starts out potentially a flower, and it changes to actually a flower. Again, it's just changing in one form. It's just changing in form, not matter. Right? Potentiality is a form it could have. Actuality is a form it currently has. Okay. So, chains of potentialities and actualities, just to list one out. I can take grass seed. Grass seed is potentially grass. I could go plant the grass. And so I could actualize grass from my grass seed. So we'll plant the grass seed. Okay, we just actualize grass. Now, grass has potential to be a cow. Not be a whole cow, be part of a cow. I should have said part of a cow here. Because the cow can eat the grass. What happens when the cow eats the grass? The grass enters the cow with the form of grass. The cow chews it, and part of that matter then becomes part of the flesh of the cow. And so the matter loses its form of grass and obtains the form of cow flesh. And it becomes part of the cow. It couldn't become part of human flesh. We can't digest grass. So the grass then becomes part of the cow's flesh. And then you can take that cow, we can kill that cow, and we can get beef from the cow. So a cow is potentially beef. And if we kill the cow, now we actualize that beef. And then we can then consume the beef ourselves, and we can convert that beef once again to human flesh. I want to focus, just bring your attention to eating for a sec, because it's a good analogy for later stuff to come. Think about what happens in eating. You take something that has a form of beef, matter that has a form of beef, you consume it, it loses its form of beef, and takes on the form of your human flesh.
Yeah.
Right? So, the matter loses one form and obtains another form. Another example, I think you're getting the point here. Acorn is potentially an oak. You can actualize that by planting it, growing it. Oak is potentially timber. You can chop down the tree and get into timber. Timber is potentially a ship. You can reorganize the timber in the shape of a ship. Here's another one that's worth going over to remind ourselves of some of his epistemology. Sense data. I can take sense data and I can form a concept of it. So you're a little kid, I show you a bunch of cats, show you a bunch of cats, show you a bunch of cats, you take in all that sense data and you come up with a concept of cat from all that sense data. Right?
Okay.
Give you a non-physical example. So sense data is potentially a cat. You can potentially construct the concept of cat from a bunch of sense data. You with me? You could also construct the concept of fur from a bunch of sense data. Take a little kid, show them this fur, show them that fur, show them that fur. They take all that sense data together, and they develop the concept of fur. And then we can use concepts to construct propositions. I can say something like, a cat has fur. And if you understood the concepts of cat and fur, you can now understand that proposition. And so concepts are potentially propositions. And similarly, we can use propositions to construct arguments. So propositions are potentially arguments. Take a bunch of propositions, put them together in the right order so that they take on the form of a syllogism, and now we have an argument. And then I take a bunch of arguments and put them together with the right form, and suddenly we have a science. So we're not limited to just talking about physical things.
Gotcha.
Good?
Yeah.
Any questions on any of that? Okay, so this notion gives us our foundation for the view that nature ultimately conforms to laws. Notice that it was potentially some things and not potentially other things. What a thing is dictates what it can be. What exactly a thing is dictates how it can change. Not anything can happen. We do not live in a universe where anything can happen, according to Aristotle. If you know what the thing is, then you know what could happen. It limits what can happen. And so you can lay a foundation now for natural laws. It's built into natural laws that oaks, or that acorns can become oaks. And somehow that's dictated by the form of that acorn. You see how it's kind of laying foundation for natural law here? Mm-hmm. Okay, so what a thing is potentially depends upon what it is actually. Or in other words, what could possibly be depends upon what actually is. Future states of, more modern way of saying it, future states of a system depend upon the current state of the system. Good? Makes perfect sense. Now, while Aristotle is completely opposed to the notion that anything can happen, he also doesn't have the same notion that science later gets of determinism in mind. He doesn't think, given this, if we perfectly set up a configuration 100 times, it's always going to execute the exact same way. Because he also knows that sometimes acorns don't become oaks, and he was kind of confused by this. I could take 2 acorns, put them in the ground, treat them identically to the best of my ability, and yet one comes out an oak and one doesn't. So it seems like natural laws happen for the most part. So he doesn't have a law in mind the same way that we now have a law of science. When I talk about the law of gravity, we mean it's universal, always happens. When he's talking about natural laws, he thinks happens always or for the most part. Because occasionally there seems to be these weird exceptions that we can't account for. Because he obviously didn't have the tools to account for it. So he doesn't have the exact same notion of natural law that we currently have in science, but for the most part would be how he sees it. Okay, so if change is matter taking on a new form, or potentiality being actualized, how does this in fact happen? So it's one thing to say that that's what change is, but how does change actually come to be? Can potentiality actualize itself? How does something that can potentially be suddenly actually be? What causes that to happen? What do we need to know to understand how change happens? So, a common example Aristotle gave was thinking about statue. Consider a change like marble becoming a statue of Plato. So, some marble changes and now it's a statue of Plato. And Aristotle says, if we want to completely understand this change, what are all the things we could possibly know about that change? So imagine you're someone who's an expert on the statue of Plato, and people come and ask you questions about it. What are all the possible things that you could tell them about the statue of Plato? Imagine you're some expert. I give you some statue, and let's pretend you're an expert on the statue, and people ask you questions about the statue. What might they ask you?
How did you make it?
How did you make it? What do you mean? Like, how did you chisel it? Like, what tools did you use?
Yeah, I guess.
Well, let's not say that you necessarily made it, but you could ask who made it, right?
Yeah.
Who made it and what did they use? Sure. So, who made it, who brought it into existence, and the tools used, that would be the efficient cause. The efficient cause is that by which a thing is changed or a thing came to be. So that would be the sculptor. What else could you ask about the statue? If you had some random statue you were presenting.
What material was it?
What's it made out of?
Yeah.
Is it marble? Is it clay? Is it bronze? What's the statue made out of? That's a material cause. That out of which a thing is changed. What else could you ask about it? Why did you make it? What purpose does it serve? Maybe they want to immortalize Plato. That is the final cause. That for the sake of which a thing is changed. And then there's one more thing you could ask about the statue. What is it? And we say it's a statue of Plato, right? What form does it have? That's the formal cause, that into which a thing is changed. So if we want to completely understand some statue that we came across, some statue of Plato, these are the questions that we could ask and the answers that we could get. We could know what's it made out of, what's the material cause. Probably should have mentioned. Cause here is kind of weird for how we're used to using the word cause. It's what enabled it to be. It's the cause of it.
Yeah.
So if there was no marble, then the statue wouldn't be able to be. So marble is a cause of the statue. It's the material cause. If there was no Plato, then we can never put the statue into the form of Plato. So that's the formal cause. So material cause, the matter of the change. The formal cause, the form the matter is put into. The efficient cause, the person carrying out the change or the entity carrying out the change. And then the final cause, the reason that the change occurred in the first place.
And this happens with all change whatsoever.
Right, so you could see how you talk about these changes and you can say, okay, I get that for man-made changes, right? If a human goes out and he does things, I can see how these four apply. But do these four apply to every possible change out there? Because if we talk about other human changes, if we talk about a chair, then we can answer all these questions once again. If it's a chair made out of wood, what's the material cause? Wood. What's the formal cause? A chair. What's the efficient cause? The man who made the chair, whoever put the chair together. What's the final cause? Maybe he wanted something to sit on while he did his homework. Maybe he was trying to sell the chair and make some money. The reason that he sat down and made the chair. So we can easily apply this to any other change, or any human change. Is there any other example of the human change you want to go over real quick?
It's a when question of when was it made?
When was it made is asking for the time stamp on it.
Yeah, that doesn't seem like a cause, right?
Yeah, so that's not what caused it to be. That's, well,
Isn't that just kind of labeling it?
that is something you could say about the statue.
It could go in the final cause, it's part of the sake of which it was changed.
For when
He built the statue of Plato to immortalize him for his birthday.
Oh, I see what you're saying. Yeah, it could go into there, but I don't know how to fit time into this picture. Because he doesn't fit time into his notion of change.
What about,
Because time is a metric of change.
what about where it is, like its position?
Where it is would be part of its form.
The formal?
Yeah, formal cause. That's part of into which a thing is changed.
Okay.
So I sculpt a statue and I move it over. Moving it over you can use a separate change if you want. Anything else?
With these human changes, does it have to be all four?
All four, he says, are present in every change.
So
Pick any change you want, and I can identify these four things for you. Or I should be able
about
to.
a caterpillar then into a butterfly.
So, now natural changes and physical changes, you might be more skeptical about these, and we'll get to those. I just wanted to start with any human change, and then we'll get further into it.
So he says that with all human change.
He says this with all change, period, but it's easiest to start with human change to get our foundation for it, and then to dive deeper and see how it applies in other cases.
Okay.
So, to completely understand the change, you must know A, the material the change started with, the matter of the change. B, the form it ended with, what it changed into. C, the agent which engendered the transition, caused it to change. Maybe that was a person. Maybe if we were talking about a change of a rock falling off of a cliff, maybe a tree fell over and bumped it and caused the rock to fall.
Okay.
In that case, the tree falling would be the efficient cause of the rock falling. And then the end or goal or the purpose of the change. This is the weirdest one for us when it comes to nature. The goal or the purpose of the change. And the fact that he includes a goal or purpose in all change is what makes him a teleologist, someone who puts an end or a goal or a purpose into everything. Everything happens for a purpose is a teleological view.
Everything has purpose.
Yes. So everything is happening toward some end, some goal, some purpose. And so we have a hard one with this one when it came to like a tree falling and hitting a rock and causing the rock to fall off an edge of a cliff, right? So that one's a weird one for us. But these other three we should be pretty okay with.
Okay.
Outside of natural change. Right?
Yeah.
Good? Okay, so change. A transition from one form to another form. Give a more full account now, accounting for these four elements. What can we call a change now? Bringing these four elements into it. Change. A transition from one form. A transition from one form. That's its material cause. To another form. That's its formal cause. By some means. That's its efficient cause. For some end or goal. That's its final cause.
Okay.
That's another way we can come to understand change. Now, does the four causes apply to natural changes, or do they only apply to artificial changes? Artificial meaning non-natural, meaning human action, result of human action. That's artificial. Example, an acorn changing into an oak, or something as simple as hitting a tennis ball. Okay, so how does the final cause come into play when there's no persons or person generating the change? Do things other than humans change for a purpose? It's useful to keep in mind, when we think about these natural changes, that Aristotle is primarily a biologist. He's not primarily a physicist, he's primarily a biologist, and this is the field of science he does the most in and pushes the furthest forward. And so, with a lot of biological changes, then it seems like there is some purpose in the change. And so, for example, if we were to look at a plant, if it had a rock right here, and you watch its roots grow down and around the rock and over here, why did its root do that? To get around the rock. For the purpose of getting around the rock. Maybe to get more water.
Yeah.
So we talk about a purpose for why the plant grew that way. Or a plant bending towards sunlight. Why is a plant bending that way? Why did it bend that way? To get more sunlight. And so we often assign purposes, in loose language, to biological factors all the time. Where we might say, you get a cut and then watch the change as it scabs. Why does it scab? To stop the bleeding, to keep infection out. As though your body had this purpose in mind in generating the change.
Okay.
Right? Or your body developing antibodies, a more sophisticated one. Why does your body develop antibodies? To fight viruses. Right? We assign some purpose to it. And so in biology, we still, very loosely, use this type of language all the time and talk about it very much the way Aristotle does. We said it does it for this purpose. Anytime we talk about an organ, we talk about it for a purpose, the thing that it serves.
Yeah.
So you see in biology, when we talk about changes in biological events, we're talking about purposes all the time, left and right, and assigning purposes to these things. As though that plant did have a purpose in mind. Or your blood did have a purpose in mind, or your body, or whatever you want to be responsible for the change, whoever you call your efficient cause.
How about that example you gave of the tree bumping over the rock, though?
The tree growing around the rock.
Not growing around, falling over and bumping the rock.
Oh, that's not a biological change.
So
That's a
how
physical
would you do
change.
with
That's
those
physical.
causes?
Well, start with biology.
Okay.
We're working from higher level to lower level. It's weird that it's easier for us to talk about in the high level than the low level. So we talk about people operating, then we talked about just living things operating, and then we'll get to non-living things operating. Consider all the organs in the human body. We always describe them in terms of their purpose, or we always ask, what's the purpose of that? What's it for? As though there was some purpose in mind in its function. It seems that living things are purpose-driven, ultimately trying to achieve their full form or actuality. When I plant an acorn, why does it sprout out roots? Ultimately, it's trying to become an oak. That's its purpose, to become an oak. And a fully actualized acorn, we would say, is an oak.
Yeah.
Right? And you can say this with any biological thing that you want to talk about. It goes through this process of trying to fully actualize. And so not only do we have it changing form from one form to another form, but we have a notion of a more developed, a more actualized being than a less actualized being. Talk about this with children all the time. When are they fully developed? When are they fully actualized?
25.
Well, I'm not really asking when. I'm pointing out, you ask these questions all the time, and it makes sense to you that we're asking these questions.
Yeah.
What's changing? They're becoming more and more actualized. They're achieving more and more of their potential.
Okay.
A baby is potentially a grown man, and that's when he's fully developed. And in that process, he's actualizing that. That's where this language comes from. Ultimately, Aristotle. So it seems that living things are purpose-driven, ultimately trying to achieve their full form or actuality. And you see with living things, it's very much that they have this ultimate form that they're trying to achieve, this ultimate actuality. Now, harder with non-living things. But living things so far kind of makes sense, right?
Yep.
Okay, so before we can continue with his metaphysics, we now need to briefly jump into his physics. And his physics is largely going to pick off where, who was it? Empedocles left off. So try and remember way, way, way back to Empedocles. This was the same image we used. Ignore the inner part here. So the blood, yellow, bile, black, all that in, and just pay attention to the outer elements. So Aristotle is going to start out with this same notion. When he starts developing his physics, he's going to start out with these same elements. So let's start out with, there's fire, earth, water, and air. And the property of air and fire is that they're hot. The property of fire and earth is that they're dry, etc. So those are naming their fundamental properties. This is where Empedocles left off developing the elements. And this is pretty much the way it stays for 2,000 years. Water, fire, earth, air. And chances are you already just in culture, because we are a product of the West, when I say what are the 4 elements, you probably would have already named those things to me before you ever came across this class. And so built into our culture that these are the 4 fundamental elements. So Aristotle is no different. He's going to use these 4 fundamental elements to talk about his notion of physics. Did I skip over these? What about non-living things? How do we explain changes in inanimate objects? To discuss this, we need to first briefly cover Aristotle's physics. Okay, Aristotle's physics kind of picks up where Empedocles left off with the same picture. There's fire, water, earth, air. Remember, he rejects the atomic theory. So these aren't fundamental atoms. And I don't think that he sees a problem with fire is potentially infinitely divisible. And same with water, same with earth, same with air. I think he'd pick up with that same notion. Potentially infinitely divisible. He said you can't actually do it, because to do an infinite number of changes would require an infinite number of time. But potentially infinitely divisible. Okay. So now we got to introduce purpose into this whole thing somehow. So Aristotle had 4 terrestrial elements. He's going to add one more element that Empedocles didn't have there. Earth, water, air, fire. And then he's going to add one celestial element, ether. So 4 terrestrial elements, 4 elements that you experience here on Earth, and then one celestial element, which we call ether. Now, how does Aristotle's view of all this work? Draw a rough picture here and then go to the diagram. He says, ultimately, so first off, he thinks that the Earth is at the center of the universe. Okay? And celestial objects, the terrestrial elements, so we'll just talk about these 4 elements for now, they naturally want to move in the directions of just up and down. You never see a rock randomly shoot to the side. If I drop a rock, where does it go? Down. If I have a clump of air and I let it go, where does it go? It depends on the medium we're in, right? Yeah. If I'm down underwater, the air goes up. If it's really cool air and I'm surrounded by warm air, the cool air goes down. But I don't release a bubble underwater and the bubble shoots off sideways. It goes up. When you light a fire, which way does the fire go? Up. When you dump out water, which way does the water go? Down. Down until it hits what? The earth. And then water doesn't go past earth. Notice earth goes past water, though. If you go drop a rock in the ocean, what happens? It keeps going down. If you drop an ocean on the earth, what happens? It sits there. It doesn't go down. You with me? Okay, so Earth naturally wants to be at the center of the universe. Earth meaning the element, not Earth meaning our Earth. Although our Earth is naturally at the center of the universe too, according to this picture. Next is water. Water naturally wants to be here, between Earth. It wants to be lower than everything else except Earth. Earth is the only thing that wants to be lower than water. So if you take water and Earth and mix them together, they'll separate, the Earth will go down and the water will go up above the Earth. And then next, you naturally want the air around the water. Air wants to be above water, and it wants to be above Earth. Water wants to be between Earth and air. And then fire wants to be here. So if you light a fire in the air, it's going to keep going up. It's going to try to get out of the air. So that's what this picture is trying to represent. You can see the Earth and the fire pretty well, but the water and the Earth might have thrown you off in that picture. So the Earth wants to be at the center, then water, then air, or then wind, air, I should say air, not wind, air, and then fire. You with me so far?
Yeah.
And then ether wants to be outside all of that. So just focusing on fire, wind, fire, water, earth, and whichever one I didn't say. For a second here. So each element has its natural resting place. And its natural resting place is actually based on, Aristotle says, its weight. The heaviest thing wants to be here. The next heaviest wants to be here. The next heaviest wants to be here. The next heaviest wants to be here. So Earth is heavier than water, so it wants to be here, and then etc. Now you can build things out of both air and earth and water and fire in whatever combinations, and that dictates where it wants to be.
Okay.
Right?
Yeah.
So if I take something that's, what's an example? They might think about wood as being like 2 parts air, 1 part water, 1 part earth. And so naturally wood wants to be between water and air. And so if you put wood on water, it floats.
Okay.
Something like that. So the combinations of these elements determines where it naturally wants to be. The more earth it wants to be, the more it wants to be at the center. And then combinations of earth and air, or earth and water wants to be there. Other combinations, other combinations. And these things naturally move up and down to try and get to where they want to be. So even if I take a rock, a big, big boulder, and I stick it up on a shelf, that big boulder really wants to be down on the ground. And it really wants to go through that air. But it can't. It doesn't know to just go to the side and fall. Because it can only go straight up and down without any other force acting on it. So the only ways that these 4 elements can move are straight up and straight down, unless other things interfere. So they really, really bad want to be where they should be. That's what he's going to describe as what we now call gravity, is saying where it really wants to be.
Okay.
So each element has its natural resting place, and that's its end. Its end is to get to its natural resting place. This is how he's going to introduce the end to it, the purpose to it. Right? So you got that tree that was up in the air. Naturally, the tree wants to be down out of the air. And so something happens inside the tree which allows it to reach its natural resting place and fall over on the ground, which hits the boulder. The boulder naturally wanted to be down at the bottom of the hill anyways, so when it hits the boulder can now go where it wants to go. So you gave a little bit of side motion, and now the boulder can do what it wants to do and try and get to its natural resting place. Everything wants to get to its natural resting place. You light a fire, it doesn't just stay there, it instantly tries going up as fast as it can. It naturally wants to be up there. That's going to be its teleology. That's going to be the purpose of the change. Why did the fire go up? Because that's where it wants to be. It wants to be at that level. Okay. Each element, blah, 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 said that. An object's natural resting place is dictated by the combination of elements in it. We already mentioned that. Okay, I think we're good with this, right?
Okay.
Okay. The 4 terrestrial elements naturally move up and down, ignoring what Aristotle calls violent motion. Violent motion is motion that violates nature. And so that's non-natural motion, that's artificial motion, that's you. So you can act violently, but a rock can't just act violently on its own. It can't violate what it naturally wants to do. So ignoring violent motion, elements naturally just move up and down. The 4 terrestrial elements. We haven't talked about the ether yet, we'll come back to that one.
Okay.
So far, just 4 terrestrial elements, before we experience here on Earth. The combinations of the elements determines the weight of an object. Now, Aristotle also noticed some other things. I take a rock and I drop it through the air. It falls pretty quick. I take a rock and I drop it in water, what happens? It falls slower. Now I take a rock, drop on rock, it doesn't fall. So, where are we? The speed an object falls, we're saying falls, but moves up and down. The speed an object moves up and down, we say falls, is proportional to its weight, which has to do with the combinations of elements in it. The combination of elements gives it its weight, right?
Yeah.
More earthy things are heavier, more fiery things are lighter, and is inversely proportional to the weight of the medium it's passing through. So the higher the weight of the medium it's passing through, the slower it falls. So syrup is more earthy than water, using Aristotle's language. And so when you drop a rock through syrup, it falls slower than it does in water. Because syrup is more earthy and therefore heavier. So syrup is heavier than water is heavier than air. And so a rock falls slower in syrup than it does in water, and slower in water than it does in air.
Yeah.
And vice versa, he thought that the medium was the only thing stopping it from falling. That's what I'm saying here. Let me go over this example real quick. A rock falls faster through air than it does through water, since water weighs more than air. The weight of the medium determines how fast an object falls. Okay, we already specified that. So coming back down here. So Aristotle thought the only thing limiting how fast an object falls is the medium it's falling through. Right?
Okay.
The lighter the medium, the less weight, the faster the object falls. And if I get an even lighter medium, it falls even faster. An even lighter medium, it falls even faster. What happens if you got rid of the medium altogether? So you had a perfect vacuum. If I drop this object through a perfect vacuum now, how fast does it fall?
Does it even fall?
How much weight is in a perfect vacuum? 0.
Okay.
The less the weight, the faster it falls.
Yeah.
Right? So he's saying roughly, speed is equal to 1 over weight of the medium. Right?
Okay.
So when the weight is big, so if we said the weight were 10, then the speed is 1/10, which is really small. If we said the weight of the medium was 1/10, then that's 1 over 1/10, which is equal to 10, which is a lot faster.
Oh, okay.
Right? So what happens if the weight of the medium is 0?
So
Or
I'm
approaching 0? If it's getting closer and closer to 0 as we're making a more and more perfect vacuum, what does the speed get closer and closer to? You calculus students, what is the limit as x approaches infinity of, or as x approaches 0 of 1 over x equal? You fell.
It's undefined.
No, it's not. We define, especially in this case, it's infinite. It gets bigger and bigger. It gets arbitrarily large. The smaller the number, the bigger it gets.
Yeah.
Right? When we plugged in 1/10, we got 10. If I plug in 1/100th, I get 100. If I plug in 1/1 trillionth, I get 1 trillion as my speed. Right? So if the weight of the medium is 0, then the speed is going to be
infinity.
infinite. Right? Instantaneous speed.
How
You
does that
follow
work?
Aristotle's logic here?
No.
Let's write some concrete examples really quick one more time. Speed 1. Let's say we're dropping it through water, and water has a weight of 10.
Okay.
So then what's the speed? 1/10.
Okay.
Meters per second doesn't matter. 1/10. You with me?
Mhm.
Speed 2. This time, we're going to drop it through air. Air is even lighter than water. Let's say air has a weight of 1/10. So what's the speed? It's 1 over 1/10, which is equal to 10. How many times does 1/10 go into 1? 10 times. You with me?
Mhm.
Okay, now let's say we drop it through fire. And let's say fire has a weight of 1/1000th. So speed 3 is when we drop it through fire. And fire has a weight of 1/1000th. So what's the speed equal to?
1,000.
1,000. And what if I remove a bunch of the fire where it's falling? So there's even less fire in there. Then we have even less weight, right?
Mhm.
So I remove some of the fire element down there. And so now the weight, S4, when we remove a bunch of the fire, or a bunch of the air, or a bunch of the water, doesn't matter what we're dropping it through, which medium you choose. But we sit there and we reduce how much is actually in the way of this thing falling to the ground. Then the speed gets higher and higher, right?
Yeah.
So what does the speed approach as we get rid of everything in its way?
Infinity.
Infinity. Or in other words, it's instantaneous.
Okay. Okay, I see his logic, but how does that work?
It doesn't work. No, this is Aristotle's physics. Okay, should have started with this. Aristotle's physics, 100% wrong.
Yeah, okay.
Okay. This is not the way it works. Okay, I see your confusion now. Sorry. Aristotle's physics, wrong. Wrong, wrong, wrong. Very, very wrong. Should have put a note in there to make sure I said that before we dived into this. Okay, now I see your confusion. So, according to Aristotle's physics then, if there's a perfect vacuum and I drop this object, it should fall instantaneously. Right? Which means the instant I drop this thing, the instant I drop it, it's still here because it's just the instant I drop it, right? But it moves instantaneously, so it's also here. So the same object is in two places at once. Impossible. So there's no such thing as a vacuum.
So what's the ether then?
We'll come to ether later. It's an element. Just like fire, water, earth, air, there's ether. And we'll come to that. But so here's Aristotle's argument that there's no such thing as a perfect vacuum. He says you can't get it.
A perfect vacuum.
A perfect vacuum.
Does he say that some vacuums can exist though?
Depends on what you mean by the word vacuum. Typically what we mean by a word vacuum is getting close to a vacuum.
I'm saying like there are vacuums in our world.
Okay. You're talking about vacuum cleaner, right?
No.
No. What are the vacuums?
Like you can create a space.
You can create an almost perfect vacuum.
Yeah.
You can pump out a bunch of the air, but can you get rid of all the air? Can you get rid of everything in there? All matter inside of a tube?
No. I don't.
Our current physicists would tell you no, there's no such thing as a perfect vacuum. Not for this reason, but they'd argue no, there's no such thing as a perfect vacuum.
And Aristotle's just saying that there aren't perfect vacuums.
Yeah, he's proving that there's no such thing as a perfect vacuum. Why is he proving that there's no such thing as a perfect vacuum? Remember, one of the people he's arguing against are the atomists. And what do the atomists say?
Only atoms in the void.
All that exists are atoms and the void. No such thing as a void. Sorry. Therefore, you're wrong.
Oh, so he's trying to disprove everyone, and this is how he disproves.
He's
the
developing
atoms.
his physics, and yep, this is how he does away with the atomists.
Okay. I'm making connections.
Can't just be atoms in the void. Okay. Yeah, I should have specified that. Sometimes it's weird listening to a teacher tell you things that aren't true. Pay attention as I tell you things that are not the way that it is. Okay. Yeah, should have put a note there. My bad. Okay, anyways. So, no such thing as vacuums. Vacuums don't exist. So the atomists, Aristotle says, are wrong. There's no such thing as void. So how can there only be atoms in the void? I didn't skip a slide, did I? I'm not sure if I hit that twice. Okay. So next. So a terrestrial object, left to its own devices, will only move up and down. And it will attempt to reach its natural resting place, assuming that there's nothing impeding its progress. Right?
Yeah.
If I took a bunch of fire, water, earth, and air and shook them up and mixed them all up together inside some like ball, all the earth would fall here, then the water on top of that, then the air on top of that, then the fire, assuming it persisted throughout it, would be up here. If it was still there, it would be trying to get up. Okay. Cover that. So, for there to be any side-to-side motion now, this is just straight up and down. For there to be any side-to-side motion, there must be some external force acting on the object. Right? So he says an object of its own accord will naturally move up and down. But in order for any side-to-side motion, there has to be some other agent acting on it. So a rock left to its own devices, that will move down. Air left to its own devices might move up. But for any side-to-side motion, you need some external force. Something applying a force to it.
Okay.
With me?
Yeah.
So he wouldn't have classified gravity as a force the same way we currently do. So all forces only produce side-to-side motions. Or if there are side-to-side motions, then there must be a force. I can also push a rock down. That's perfectly fine. But if a rock's moving side-to-side, we know there's some external force acting on the rock. Okay, the side-to-side motion only exists while an external force is being applied. This is false, but Aristotle's physics. Side-to-side motion only exists while a force is being applied, and the side-to-side velocity is proportional to the force on it. So let's set up a scenario to help you understand why Aristotle thought this, even though it's wrong. So imagine that here's you. You're pushing that box, right? You're pushing it, pushing it, pushing it. What happens when you stop pushing it?
It goes a little bit.
Yeah, but it stops.
Yeah.
Pretty quick, it just stops. So Aristotle says, if you want to keep it moving, you have to keep pushing it.
Yeah.
So it takes a force to maintain a velocity. False, but that's what he says. Now let's imagine another scenario. You're pushing a box that weighs 10 pounds. I'm over here. I'm pushing a box that weighs 20 pounds. And let's say you and I are moving the boxes the exact same fast. Aristotle says, I must be pushing twice as hard as you. Okay? That's what he means. So, let's read this now again and hopefully you get it. The side-to-side motion only exists while an external force is being applied. And on top of that, and the side-to-side velocity is proportional to the force on it. So if I want to, I should have said this example. Sorry. You and I are both pushing a box the same way, but let's say I'm pushing a box so it's going twice as fast as you. You're pushing your box and it's only going 10 meters per second. I'm pushing a box that weighs the exact same amount and my box is going 20 meters per second. Aristotle says I must be pushing twice as hard as you.
But that's not the case, right?
No, this is not the case. We'll get to Newton's basic laws of motion. Do we need to just establish these really quick? Newton's laws of motion. So Aristotle says force is equal to mass times velocity in modern language. Newton says, no, Aristotle. Force is equal to mass times acceleration. Aristotle says, if I want to keep an object moving sideways, I have to keep pushing it. Newton says, no, an object in motion remains in motion unless acted upon by a force. So now that we have a notion of outer space, which Aristotle obviously didn't have, think about this thing, and if I throw it that way, so it's going that way 1 meter per second. When's it going to stop?
It's not.
It's never going to stop unless another force acts on it. An object in motion remains in motion unless acted upon by a force. And if you're going to change its force, you need to apply an acceleration, not a velocity. So Aristotle thinks for an object to remain in motion, there must be a constant force pushing it.
Interesting. Okay.
Okay. We'll get to Newton's three laws. It'll be one of the first things we do when we do physics.
Fun.
But you see why physics is so great. Yeah, we'll fix all that. Anyways, Aristotle said this. Now, he had to deal with some weird cases, which I think one of you already talked about. What about when I throw this? How does Aristotle explain that? Because this is one that confused him a lot. So when I take this thing and I throw it through the air, it keeps moving sideways long after my hands stop pushing it. How does it keep moving sideways?
Does he say the air just acts on it?
Yeah, so in his mind, you create like some sort of vortex around this thing, and so the air coming back in to fill the space it clears out keeps pushing it, pushing it, pushing it. And it's the air pushing it. So he thinks if you had a perfect vacuum, like kind of like outer space, and you tried to throw the object, it'd instantly stop if there's no medium. Obviously, he didn't have outer space to think about.
How does he explain the fact that it's not staying the same then? Because if the air was
It's moving down because it naturally wants to go down. That's natural motion. The side-to-side motion is due to the fact that you threw it and the air is still pushing on it.
Oh, I see. Okay.
So the down motion was already explained. It's just how does it keep going to the side once I let go of it? And that's because the air keeps pushing it somehow. So, yeah, he didn't like that explanation, but that was the best he could come up with. Now remember, he's ultimately a biologist. This is stuff that this is just one of the many things he's doing. So he points out where he feels like there's holes in his physics, and he makes it very clear. He's not trying to be tricky and hide his mess from you. He makes it very clear. This is something messy in my physics that I can't figure out. But this is the way it seems to be to me. And obviously, the fact that you were getting a little confused shows how much it just appeals to your natural intuition. So everything he's saying seems perfectly reasonable. And it's not surprising that someone would believe us, because everyone believed it for a long, long time.
Okay.
Anyways, for projectile motion, the medium carries the force. We already said that. Okay. So we did all that. Next. Now let's get to ether and celestial objects. Now, celestial objects for Aristotle start with the moon outwards. So the moon's the first celestial object. Anything closer than that, he would call terrestrial.
Okay.
Good? So the moon, the sun, and the stars are composed of ether. They can't be composed of earth, because otherwise they come falling in on us. Right?
Yep. Okay.
And notice that all these things move in a very peculiar direction. Which way does the moon move? It doesn't fall in. It moves which way?
Around us.
It moves in a circle.
Yeah.
The moon moves in a circle. The earth, or the sun moves in a circle. The stars move in a circle. Everything moves in a circle. If you go out and watch them, ignore all your scientific experience, and now just think about what you personally could observe with your own eyes. Imagine you never had any education, you grew up on a desert island, and you watch these things come by. You would think that the moon moves in a circle around the earth, the sun moves in a circle around the earth, and if you stare and look at the stars, it looks like they're spinning. Long enough, right?
Yeah.
Right. So, the same way that terrestrial objects naturally want to move up and down, celestial objects, things composed of ether, naturally want to move in circular motion. So things composed of ether naturally move in circular motion. Things composed of fire, water, earth, and air naturally move in up and down motion.
Okay.
So for Aristotle, if you were to ask him, why does the moon go around the sun? He'd say, why does this object fall when I let it go? It's just the nature of things.
Okay.
So both of those are just as natural to him. Okay, so what about celestial objects? Aristotle knew as a matter of and here's the crazy thing. Here's one of the reasons Aristotle thought this. Because think about back in his day, what could you know about how these objects move? So he knew that it was a matter of record that the heavenly objects have always been traveling in circles. He can go read from thousands of years ago, charting that the Egyptians did, of how these things were moving. And circles, circles, always circles. Seems like they've been moving in circles for eternity. Relative to him, they always have been and always would be moving in circles like this. You got to go back and think about how these ancients saw the universe. The moon always had been and always would be. The sun always had been and always would be. There's no reason for them to think that these things had a beginning or would have an end. The universe always has been and always will be the way that it is from the moon and beyond. Maybe things here on the earth change, but everything in the heavens just keeps following the exact same pattern over and over and over again. Very cyclical.
Okay.
And so it seemed pretty natural that they're all just moving in circles. It's the only eternal motion that you could have forever. Right? If you had any linear motion, it has to have a start and an end. Because they also thought the universe was finite in size. So the only infinite motion you could have in a finite universe is circular motion. So he knew it was a matter of record that the heavens have always been acting this way, always and forever. So that just must naturally be how they behave. They just move in circles. Therefore, they must be composed of some new element, ether, one whose natural motion isn't up and down, but rather circular.
Okay.
So Aristotle argued against the harmony of the spheres. This is just a quick cool side note to show you some of his thinking. The harmony of the spheres, you remember that this was a Pythagorean notion. The Pythagoreans knew that regular movement creates sound, right? And so here we had these big objects flying through space super fast, like the moon, the sun, the stars. So they must be creating sound. And then their argument was you couldn't hear this sound because you've always heard the sound. And so you don't know what silence is. And so you have nothing to contrast it with. It's kind of like someone who says a fish doesn't know it's in water.
Yeah.
Yeah, so a fish can't comprehend that it's in water because it's always been in water. You can't hear these sounds because you've always heard these sounds. Now, Aristotle didn't like this. He says, first of all, okay, you can't hear it. Fine. Let's pretend for a second that they are there. We know that sounds have physical effects on things. I can feel my voice, and the more intense I talk, the more I can feel it. You know that you can use sound to shake things. You've seen the opera girl break a glass when she hits a certain pitch in her voice. You can use sound to break things. Sounds have physical effects. Now, if you're saying that these massive objects are making massive sounds traveling all the way through us, there should be some sort of vibration. There should be some effect, something I can measure. Maybe I can't hear it, but I should see something shaking, shouldn't I?
Okay.
So Aristotle asks, what's the difference between a harmony no one can hear and that has no physical effect on the world, and no harmony at all? You see what he's saying?
I think so.
So he gives his arguments why he thinks they're wrong. This is very typical of Aristotle. First, he gives the argument why he thinks you're wrong. He says, even if you're right, it doesn't matter. Very common type of argument that he gives. So he argues against, no, if there were, then we should be seeing these side effects. And even if, okay, they produce no side effects, then it's completely pointless that they do that, because there's no way to know.
Yeah.
You may as well talk about a unicorn's favorite food. Right? And then, just to one more note, because we're going to introduce some more of Aristotle's confusion here in a second. They also knew the order of the celestial objects in their distance, in which ones were closer to the Earth. They didn't know the distance to the stars and to the sun and to the moon and stuff, but they knew the order that these things were in, because they could see when they pass each other.
Okay.
Kind of. So they thought that the order went the moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn. They thought that was the order of the planets, and you can see why, if we draw a rough picture of the solar system, why they would think that. So here's the Sun, here's Mercury, here's Venus, here's the Earth, and so you can see that there would be a point in their orbits where you can see that it went. I think I might have written those in the wrong order. I think they had these two switched, but now I'm not sure. Because they could have seen it two ways. They could have seen Venus come between them and Mercury, and they could have also seen it over here where Mercury comes in between them and Venus.
It's probably Venus, since that's the morning and the evening star.
Yeah, I would guess that they thought Earth, Venus, Mercury, so I bet that those two need switched. The moon's right here going around the Earth, right? There's the moon. That one's obviously the closest. So the moon, Venus, Mercury, the sun, and then further away were Jupiter and Saturn going around. So that's what they thought the order of the planets were. Make sense?
Yeah.
And kind of makes sense why they thought that?
Yeah.
And you can see why they're a little bit confused about the planets. Because in their picture, everything goes around the Earth. I was drawing the actual, how I would actually think about now. Oops, I just realized I drew outside the camera space. Anyways, so that's the order that they thought that the planets went in. And then the furthest out is the stars. Now, one more thing to know, maybe I made a note about where to talk about it later. Maybe we just talk about it later. Okay, so now let's talk about why Aristotle thought that the Earth was at the center of the universe. First off, it helps him explain motion. His whole theory about motion puts the Earth at the center of the universe, right?
That makes sense.
Aristotle thought if you picked up the whole Earth and shifted it a foot to the right, it would fall back. Right? It wants to be at the center of the universe.
Okay.
It's naturally going towards the center of the universe. So that's one reason he thought it. Now, there was another theory in his day that the Earth is actually going around the sun. Someone did think this. And so, some person who thinks they're clever says, Copernicus wasn't the first one to say that. Ancient Greeks thought that the Earth went around the sun. Yeah, they did, but in the worst kind of way. Some ancient Greeks thought that the Earth went around the sun once every day, not once a year. In reality, the Earth is spinning, and that's what makes it look like it. So they were not right. Or they were right, but they were right in an awful way. The Earth definitely does not go around the sun once a day.
Yeah.
But this was a competing theory that Aristotle had to deal with. So here was the question. Does the Earth go around the sun, or does the sun go around the Earth? Now, no one at the time was thinking the Earth going around the sun in 1 year. No one was thinking that. This was all in one day. So was it the Earth going around the sun in 1 day, or the sun going around the Earth in 1 day? Those were the two competing theories.
Okay.
Okay? So, Copernicus was a huge leap forward in how he laid out the solar system. which is another 1,700 years. So Aristotle viewed the Earth as the center of the universe. If you shift the whole Earth some position, it would fall back to the center of the universe. He suspected that the further away so we'll get to that. That one's down here. He also suspected that the further away from the Earth an object is, the more perfectly spherical its path should be, and so he was confused by the planets. So let's make sense of this for a second. Nothing more moves more perfectly. Well, we also need to talk about the spheres. Let's talk about the spheres for 1 second. So the celestial object, talking about like the moon, Aristotle did not, nor did any of the ancients, think about the moon as just moving in a circle, as a standalone object by itself. They thought about the moon as on a big sphere that's transparent. And the moon is a part of that sphere. And the whole sphere orbits. So it's like one big glass sphere with the moon as part hooked onto the sphere, as a spherical object on the sphere.
So you're like, there's this massive casing around the Earth.
Right, it's like a big, thick glass casing
Okay.
with the moon stuck in that glass. And that sphere is rotating. Same with Mercury, same with Venus. So it's these spheres orbiting that are causing it to look like the moon's moving in a circular path. So it's not really the moon as a standalone object moving in a circular path, it's a whole sphere that's a part of rotating. So you have the Earth, and then you have a sphere around the Earth, which contains the moon, and then you have a sphere around that, which contains Mercury, and one that contains Venus, then Mercury, most likely, and then the sphere that contains the Sun, and then the sphere that contains Jupiter, and then the sphere that contains Saturn, and then the most outer sphere contains the stars. Because if you were to go stare at the stars long enough, it just looks like one big sphere painted around the Earth with a bunch of stars painted on it that's spinning. That's what it looks like. So it's a bunch of these spheres. That's what we mean by the spheres. And the harmony of the spheres was referencing those outer spheres spinning. Okay, so that's what we mean by the spheres. And some of the spheres are more perfect than other spheres. Aristotle thought that the further out the sphere, the more perfectly circular it should be. So we thought that the stars should move in the most perfectly circular motion,
Okay.
and the moon should move in the least perfectly spherical motion.
Why is that?
Well, he just thought that that seemed natural. That the further away from Earth it is, the more perfect and eternal it is. And so the more perfectly circular it should be. The more ether it should be.
Okay.
Get it further away from the Earth, it's more etherish, less contaminated, more perfect. So this is what really confused him about the planets. Because relative to the Earth, the stars move in a perfect sphere, the sun moves in a perfect sphere, and the moon moves in a pretty perfect sphere. And it's the planets that don't look like they move in perfect spheres around the Earth. And that's because of the orbits of the planets, right?
Yeah.
So it makes sense why he was so confused. So he points out this is one of the problems that he hasn't been able to figure out. Why the planets look like they're moving in such weird motions around the Earth rather than in these perfect spheres. But something as close as the moon is moving almost perfectly circular. The stars are moving almost perfectly circular. But then Venus is moving in a skewampus path. What's going on?
So he just left it at that?
Yeah, so he pointed out that's a problem. He didn't know what to do with it. It's a fact. Watch how it moves. It's weird. It's not a perfect circle. I don't know what to make of it.
What about the moon's phasing?
The moon's phasing?
Yeah, like how it goes from full moon to the new moon.
Oh, he was suspected that that's the sun shining on it.
Really?
Uh-huh. You can still think about moon phases fine. Think about the Earth at the center. And you still think about the Earth here, the sun way out here, and the moon right here. And when the moon's right here, relative to the sun, you can see full moon relative to us. If the moon were right here, the sun's shining on that half, so if you're on the Earth now, you can only see half the moon. And he knew that when the moon blocks out the sun, you can't see the moon, an eclipse. So yeah, they had a perfectly valid explanation for the phases of the moon. It doesn't break anything to say that the Earth's at the center of the universe for phases of the moon. Still works. Okay, so how did he do away with this theory about the Earth going around the sun in one day, though? So he had to decide, is it the Earth goes around the sun in one day, or the sun goes around the Earth in one day? Which of these theories makes more sense? And he says, he thought it was that the sun goes around the Earth, not the Earth goes around the sun. And he gives his argument why. And it's because there's no stellar parallax. Now, what's a parallax? So, I can only do it with one of you at a time. If I put my arm lined up right here with Peter, and I stand a little bit on this side of my arm, then relative to my arm, Peter's on the right-hand side of it. You with me? Now, if I shift a little to the left, now Peter looks like he's on the left-hand side of my arm. So notice, if my arm's holding still in space, and Peter's holding still in space, and if I shift side to side like this, then when I'm over here, Peter looks like he's on the right side of my arm. When I'm over here, Peter looks like he's on the left side of my arm. Same thing here. So, pick a star and pick some other star relative to that star. This is just looking at the night sky, but parallax effect. So Aristotle's saying, look, if the sun's going around the Earth in one day, then we should be able to measure this over a 12-hour period really easy. I should be right here, pick some star, and then see some star that looks like it's on the right of it when I'm over here. And then after 12 hours, look at it and see that same star look like now it's on the left of it. And so how the night sky looks to me, it should at one instant look like this, and another instant look like this. And yet the stars look perfectly fixed. There's no parallax effects that we can measure. Now, in reality, there is a slight one. Obviously, he wasn't expecting it over an entire year, and I doubt that they have the tools to measure it because the stars are also way far away than the Greeks would have ever guessed. But that's one of the arguments he had for why the Earth must not be going around the sun. Because then we should see this effect, which we don't really see this effect. Definitely not in a 12-hour period. So that was one of his arguments against, and you can see that's a pretty clever argument. So he gives these things thought. He thinks back to data, things that he can actually observe, how the universe should be if you're right, and how the universe should be if I'm right. And it looks like I'm right and you're wrong. Sorry. Okay. So that was one of his core arguments. Okay. Oh, they did think Mercury than Venus. So they must have had a time where they watched Mercury pass Venus to figure out which one was closer. Anyways, so here's roughly how, not Aristotle, but someone's right after Aristotle, Ptolemy, one of his students. I think it was a student, might have been the son of his student. Once the Ptolemies start, they all just name themselves Ptolemy. So I'm not sure which Ptolemy it is, and I don't even think it's Ptolemy himself. I think he hired someone and just named the model after him, some mathematician.
Okay, totally non-related question. Do you have keys to get into the building?
No.
I may have to move them unless there's a bathroom nearby.
Yeah, there's not. It's been 2 hours. We can cap it off here and come back and start here next time, picking up with Aristotle's physics. So we'll end off here. We'll get more into his model of the universe, how he saw things, then get back and finish his metaphysics next time, and hopefully get through his psychology as well. So, call it there.
Oh, his psychology is going over the mental stuff.